project will deal with computer simulation of mobile compartment file. As far as we know, this simulation...
So, we do not hear you. Stop, we will begin again. It works? Okay. Can you stay here? Because, okay. Can you stand here? Because I see people don't see. Okay. That's better.
Okay. Our project deals with computer simulation of automobile engine compartment files by FDS.
Excuse me, do you hear? No, there is a problem. Can you arrange that, please? No?
As far as we know,
Did you hear better?
Yeah.
Okay.
As far as we know, this simulation has not been studied and published until now. This AutoFund was part of larger project dealing with automobile and automobile files. The institution participating in this project were Institute of Informatics of Slovak Academy of Sciences, the Faculty of Special Engineering at the University of Žilina, and Mathematical Institute Slovak Academy of Sciences. This project included both full-scale simulation and subsequent computer simulation of different fire scenarios with the aim to evaluate risk and possible impact of these fires. In the framework of the project, a series of full-scale experiments were performed. They dealt with engine compartment fire, passenger compartment fire, ignition of automobile bodywork from early-burning automobiles, and also with some aspects of fires in garages and tunnels. The problem of engine compartment fire itself is important because of increasing number of automobiles which constitute a significant threat of fire, and the most common source of the fire is the engine compartment. The proper fire description includes both full-scale experiment and computer simulation. Full-scale experiment about engine compartment fire was conducted in Fire Protection College of the Ministry of Interior of Slovak Republic in Považský Chromec in the year 2009. Automobile Audi 80 with slightly distorted bodywork and missing front lights was used in this experiment. The aim of the experiment was to gather data for validation of computer simulation of different fire automobile scenarios. Here we can see the configuration of this experiment. The automobile was placed on the concrete surface area and surrounded by measuring devices. Several physical quantities were measured during this experiment. The most important were 3 thermocouples, which were placed on the upper part of the engine block, in front part of the dashboard and above the automobile. Moreover, surface of the bonnet was recorded by infrared camera, which was placed in front of the automobile. The experiment was observed also with another digital cameras, and basic meteorological data were also collected. Here we can see the photo of the engine compartment. The most important components are the air filter in the left side, the rubber tube, and some plastic components in the rear part of the engine compartment. The behavior of this experimental fire was as follows. The fire was ignited by burning of a small amount of gasoline put onto a small cloth which was placed under the rubber tube. During the first 3 minutes, smoke at the right side of the bonnet and from below the front window was observed. At the 4th minute, the smoke appeared from the holes at the place of missing front lines, and it became more intensive. Varnish ignition occurred between the 7th and the 8th minute, and after 12 minutes, the fire was extinguished. Here you can see the behavior of this fire. The impact of the fire was considerable. There were some components which were completely burned, mainly the rubber tube, 3 plastic tanks in the right rear part of the engine compartment and the air filter box, and several other plastic components. Some components burned partially, some smaller plastic tanks and other components, and the engine block was partially burned. Here we can see the photo of the impacts of this fire. Here is the whole gap where was the burnt air filter and other components. The next step of our work was computer simulation of the engine compartment fire. We elaborated an input geometry for FDS. Some components in this geometry were modeled realistically and some modeled by approximation. For example, the motor tube was modeled as the cluster of thin strips which had the same mass and surface to volume ratio as was the original one. 5 prevailing types of materials were identified inside the engine compartment: aluminum alloy for engine block and bonnet, the rubber for the tube, polyethylene for plastic tanks and other plastic components, and paper for air filter content inside the air filter. On the outer side of the engine compartment, the bodywork was covered by varnish. Here is the scheme of the engine compartment for FDS. These are the crucial components of this fire, and here is the starting fire. Here is placed the thermocouple, measuring the temperature inside the engine compartment. We performed 3 types of simulation. Simulation A includes the interior of engine compartment and the lid. Simulation B includes also an additional space above the engine compartment, and the simulation C includes complete front part of the automobile which is placed into open space. Here we can see the computational domain for the simulation A. It contains about 500,000 cells with the resolution 1 centimeter. 650 seconds of simulation took 180 hours of CPU time. Later I will show the video from this simulation. Simulation B includes moreover the one additional mesh above the engine compartment with about 200,000 additional cells. The duration of this simulation was the same as in the simulation A. I will show these AVI files later. The behavior of simulated fire was as follows. From the 1st to the 4th minute, an ascending airflow in the rear part of the compartment was formed, and fire spread along the rubber tube to the rear part. At the 5th minute, the plastic components in the rear part of the engine compartment burned away, which caused significant increase of air supply, and the air filter started to burn more intensively. It occurred between the 5th and the 10th minute. Between the 7th and the 8th minute, there is a mistake. The varnish ignition occurred. Now, here we can see the comparison of surface temperature distribution by infrared camera and by the simulation. As we can see, there is a reasonable agreement between these patterns. Also, the time of the varnish ignition is the same. Here are the experimental temperatures of the fire. The most important tendencies are this increase at the 300 seconds in the gas temperature inside the engine compartment, and the gradual, almost linear increase in the temperature of the bonnet. As we can see, our simulation reproduced these tendencies with success. Here is this abrupt increase at the 300 seconds and the development of the bonnet temperature. Now I can show these videos. This is the behavior of the simulation A. During this simulation, the fire was located inside the engine compartment. Here we can see the burning out of the components in the rear part of the engine compartment. Here is the simulation B. It shows the flame spread above the engine compartment, above the space on the bonnet. Which is my presentation. And finally, the simulation C includes the whole front part of the automobile. It has the highest computational requirements. Therefore, this work is getting. We are working on this simulation. That's all. Thank you for your attention.
Thank you. Is there some questions? Yes?
Thank you. Could you tell me, please, what is the total heat release rate of a burning car? Maybe measured or in your simulation?
Did not have measured the heat release rate, but according to our simulation, the heat release rate is in the range 50 to 100 kilowatts inside the engine compartment.
Not on the whole.
When it burns, it could be 200 kilowatts approximately. It differs by.
But the wheels does not burn? The wheel does not burn?